continue with the course on biostatistics and design of experiments. We have been talking about 2 sample t-tests in the previous class. Basically 2 sample t-tests means we have 2 sets of samples, that means you are comparing drug A with drug B, or you are comparing 2 different plants for their yields. So, we take samples and then we want to find out whether those 2 samples come from the same population or they are from different population. So, let us look at some more problems in that 2 sample t-test. So, a sleep inducing drug was given to 30 subjects, okay. So, 30 subjects here, and at the same time a placebo was given to 33 subjects, you have it here actually, okay. And the time taken for them to get into the sleep was monitored actually. So, for example, if you look here, we are given 15 minutes, 25 minutes, 30 minutes, that means it took some volunteers 15 minutes to sleep when they took 2 volunteers when they took placebo, and 0 volunteers when they took the drug. So, it took 4 volunteers who took the drug to sleep in 25 minutes, and it took 3 volunteers to get into sleep after 25 minutes. So, that is what these numbers are actually. So, these numbers are number of people who took so much minutes to sleep. Now, the question is, did the drug lead to quicker onset of sleep? That means I want to know, okay, whether the average time taken to sleep by the drug people is less than the average time taken for the placebo group at 95% confidence interval, okay. So, it is quite simple. So, we have 30 volunteers who took the drug, and we have 33 volunteers who took the placebo, and this is the time. So, we can use the equation which I talked about in the previous class, okay. So, we need to calculate T is equal to XH minus XL, that means XH is your mean for one group, and this is the mean for another group, divided by SP square root of 1 by NH, that means NH is number of samples for one group and NL is the number of samples for another group, okay. And then where SP is given by NH minus 1 SH square. So, SH is the standard deviation for the first group, SL is the standard deviation for the second group, okay. And this is called the T calculated. If the T calculated is less than the table T, accept H naught. If T calculated is greater than the table T, then reject H naught. The degrees of freedom is equal to NH minus 1 plus NL minus 2. So, this in this particular problem it will be 63 minus 2, 61 will be the degrees of freedom. Now, what is the hypothesis? The null hypothesis H naught will be, okay, mu A is equal to mu B, okay, that is the null hypothesis. That means both the drug A could be the drug, B could be your placebo. Now, the alternate hypothesis could be mu A less than mu B. So, B could be your placebo, A could be your drug. So, it is a 2 sample, okay, one tail, because we are talking about alternate is mu A less than mu B, okay. So, it is a one tail or single tail, 95% confidence interval. So, we have to use this equation, okay, to calculate T, and then compare it with the table T. If this T is less than the table T, we accept H naught for 95% confidence, that is P is equal to 0.05 one tail test. If it is less than, the T calculated here is greater than table T, then you reject the H naught. Okay, so, we can use a Excel like software to calculate all these parameters, the mean, the standard deviation of the individual samples, all these things, okay. That is what we are going to do. So, this is again I am showing you the problem here, time taken to sleep in minutes, number of subjects who took this drug, number of subjects who took the placebo, okay. So, I need to calculate the average of each set. So, how do I do? So, I will do 15 into 0 this, 15 into 2 is for the placebo, 25 into 4 is here, 25 into 3 is here. So, like that I do go down, 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 and then I do all the summation here, and then here I divide by 30 because there are 30 people who took the drug, then here I divide by 33. So, it took 40.5 minutes on an average for the subjects who took a drug to get into sleep, whereas it took 43 minutes for subjects who took placebo. Now, the question is is 43 and 40 appears to be different, but is 40.5 is statistically less than 43 at 95% confidence interval. Okay. So, now we need to calculate the standard deviation of each set. Okay. Then we need to calculate this NH minus 1, that means here it could be 30 minus 1, NL minus 1 could be 33 minus 1. Okay. Then standard deviation square, that is variance, take the square root, substitute here, and then calculate the T calculator, and that is what I am doing in this part of the sheet. Okay. So, what do? I take average, this is my average is 40, okay. Then I will take the individual value, okay, individual value, and then multiply it by the, then square it and then multiply it by the, okay, number of candidates. Okay. So, here it will be 40 minus 15 square multiplied by here 0, whereas in this for the other, for the placebo I will do 43.03 minus 15 square multiplied by 2, like that I keep on doing down, okay. Okay. Then I will do the summation, then I will do the overall summation, okay. Then I can calculate the 251 is what I am getting here, okay, 251 is what I am getting here, and then that is multiplied by 1 by 30 plus 1 by 33, that is this term here, okay, and then I am taking a square root here, you can see here square root, and then I am doing the difference is 2.5 because SH minus XL you have, so the difference is 2.5 and the denominator is 3.99, so T comes out to be 0.633. Now, is this T statistically T less than the table T or greater than the table T for 61 degrees of freedom for P 0.05 one tail test? Now, I go to this, it is a one tail test 0.05, okay. So, I go down 61, so it is 1.645, okay. So, we can even take, so obviously this T calculated is much less than the T table. So, we cannot reject the null hypothesis, that means there is no statistically significant difference at 95% confidence limit between the placebo and the drug. Okay. So, although it looks visually there is a decrease of 2.5 minutes on an average for people who have taken the drug when compared to placebo to go to sleep, but when you do this analysis we find that there is no statistically significant difference at 95% confidence. So, there is no reason for you to reject the null hypothesis. So, you understand this problem. So, we make use of this equation, the equation is XH bar minus XL bar, that means mean of sample 1, mean of sample 2. So, if you call it this, then NH is the number of items in that sample 1, this is the number of items in the sample 2, okay, and SP is the standard error which you calculate using this formula. So, these are the individual variances for the sample 1, the sample 2, okay. The degrees of freedom here will be NH plus NL minus 2. Then you calculate T from this, that is called T calculated, then we use the table T, and then if the T calculated is less than the table T, we cannot, there is no reason for you to reject null hypothesis, that means you have to accept null hypothesis. Only if the T calculated is greater than table T, then we reject the null hypothesis, then we accept the alternate hypothesis. In this particular case we want to know whether the drug reduces the onset of sleep, okay. So, your hypothesis are null hypothesis is mu A equal to mu B, if I call A as my drug and B as my placebo, and the alternate hypothesis is mu A is less than mu B, okay. So, how do we calculate each of these? It is quite simple. Let me first talk about the averages, how do you calculate averages. So, what do you do? 15 into 0, 25 into 4, like that you keep on doing it, okay. Then you sum it up and then divided by 30, that will give you the average time taken for the people who took the drug. So, for the placebo you do 15 into 2, 25 into 3, 30 into 3 and so on, again you add it up and then divide by 33, you get the average as 43.03. So, you can call it XH bar, this is XL bar, okay. NH will be 30, NL will be 33. Now, how do you calculate the variances here? what do you do? If you want to look at the drug part of it, so we say 40.5 minus 15 square multiplied by the number here in this case 0, then 40.5 minus 25 square multiplied by 4 people, 40.5 minus 30 square multiplied by 3, okay, that is what you are writing here. Then here 40.5 minus 35 square into 6, that is what you are writing. So like that you keep on doing for the drug. And for the placebo, what do you do? You take 43.03, okay, multiply minus 15 square multiplied by 2, that is what comes here. 43.03 minus 25 square multiplied by 3, that is what comes here, and so on. And then you add up, you end up like this, okay. And then you can calculate this term because you got this, okay. And then finally you end up with the 251 is not divided by 1 by 30 plus 1 by 33, that is nothing but this, okay, because 30 is the number of samples for the drug and 33 is the number of samples for placebo. Then you are taking the square root, that comes to 3.99, so that will cover the entire denominator part of it. The numerator is 2.5, right, that is the difference in the averages. So you divide 2.5 by 3.99, you will get 0.633. So that is the table T, and according to that will be your calculated T, and table T I have written as 1.96, but actually it should be if I take 95 percent or point P as 0.05 and I take one tail test, I should be reading here, so it should be 1.645, not 1.96. So this should read as 1.645. So obviously whether it is 1.645 or 1.96, obviously the table T is much higher than your calculated T. So obviously there is no reason for you to reject the null hypothesis at 95% confidence interval. So that means the drug does not reduce the onset of sleeping time when compared to the placebo, okay. So you understand how to do this problem, very interesting. We come across these type of problems quite a lot when you are performing clinical trials. It could be placebo, it could be drug B, that means another drug. So you may be comparing two drugs in the market and so on actually. Okay. So this table is very important. This top portion is related to the one tail, the bottom portion is related to two tail. So when we say one tail 0.05, you have to read this column. If you say two tail 0.05, you have to read this column, please remember that, okay. So what is the relationship between two tail and one tail? Two tail is total is 0.05, so each side will be 0.025, okay. So that is the relationship here, understand, okay. Or we can use this another table, this gives you the outside portion here, okay. Again you can see 0.025 relates to one tail, so for two tail it is 0.05, so 1.96 is the T value. Okay, let us look at another problem, another interesting problem. Artificial valve was placed in rats and mouse for 30 days, they were removed and tested for wear. Okay, this is very common when you are doing biomaterial design, when you are creating new material, you keep it in animal models and then see the mechanical strength, changes in mechanical strength, which could be tensile, compression, wear, tear and so on actually. So artificial valves were placed in rats and mouse for 30 days and they were after 30 days were measured with the standard deviation. So it is all given, it is not raw data, but somebody has already done it and they are given it there. Can it be said that the wear is less when the valves are placed in rats? Okay, so this is again a one sample t test, okay, because we are trying to look at wear is less when the valves are placed in rats, okay. So rats will be less than the mouse, okay. So obviously it is a one sample t test, we can look at 95 or 99 depending upon the importance, okay. So the null hypothesis will be mu rats is equal to mu mouse, the alternate hypothesis will be mu rats less than mu mouse, okay. That is what is alternate hypothesis, say 99 or 95 or whatever you fit, okay. This is what I have said. H naught mu rat is equal to mu m mouse, mu rat is less than mu m. Okay. So, we are talking about one tail test. Obviously, the degrees of freedom is 16, 10 plus 8 minus 2 I said, if you remember. So, 16 degrees of freedom, one tail test, p is equal to 0.05, you go here 16 degrees of freedom, you can read out 1.746. Okay. 1.746. So, whatever calculation we do, if the t value we get through calculation is greater than 1.746, then we can say we reject the null hypothesis. If the t value we calculate is less than 1.746, then there is no reason for you to reject the null hypothesis at 95% confidence interval. Okay, so, we use the same equation, if you remember, xh bar minus xl bar divided by sp square root of 1 by nh plus 1 by nl, where sp is given by, right. So, we can take rats here, nr minus 1. So, nr for rats is 10, nm for mouse is 8, the degrees of freedom is 16, 10 plus 8 minus 2, then the standard deviation is given for rats. Okay. So, squaring that, standard deviation for mouse is given, squaring that, here we put 9, here we put 7 divided by, okay, 9 plus 7. So, we get sp is equal to all these number. Okay, now, if you remember, t is equal to xr minus xm bars, that means average divided by sp, this whole thing which you have calculated here. Now, xr is given by this, xm is given by this. So, divided by, we are taking this, then we are taking a square root of 1 by 10 plus 1 by 8, we get 6.89. Okay. So, obviously, the t value we calculate is much larger than the table t. So, we reject the null hypothesis at 95% confidence interval. Okay. So, then we accept the alternate hypothesis. Please note there is a minus here because I have taken rat minus xm and the rat numbers are smaller. Now, even if you look at 99% single tail test, well, let us look at 99% single tail test, that is, you look here, that is 0.01, okay, 10 plus 8 minus 2 is 16. So, let us look here, 2.583. Okay. So, 2.583 is still 2.583 is still smaller than 6.89. So, even at 99% confidence interval, we can reject the null hypothesis. Okay. So, whether it is 95 or 99, we can reject the null hypothesis, that means you accept the alternate hypothesis. So, there is a statistically significant difference, that means the wear is much more in rats than in mouse of the artificial wear. So, you see, we have done a lot of these type of problems. I have been showing you quite a lot. You can use simple Excel if the and do all these calculation. All you need to know is these set of equations here. You can use the t test function that is available in Excel, where when you have the raw data for set of samples and another raw data for another set of samples, and the t test function that is available in Excel, you can do something called the 2 sample t test when the variance are equal, and the 2 sample t test the variance are not equal. But that t test function cannot do this type of calculation, because in this data raw data is not given, the average wear and standard deviation are already given, whereas that Excel function t test can be done only when we have the raw data. So, if you have data like this, then obviously you have to use these equations, remember that. And you cannot use the GraphPad online software also. If you have data like this, you have to use these equations. That is why I am spending a lot of time on these equations. That way you get an idea about the underlying mathematics behind calculating the t. Otherwise softwares can blindly give you some t, and then it can tell you it is statistically not significant or statistically significant. So, anybody can do that, but you need to know what are the underlying equations that are used when you calculate 2 sample t test or 1 sample t test or confidence interval. That is why I am spending a lot of time on these equations. Okay. And for example, this type of problem you cannot do it with the Excel. You have to do it manually like this. You have to take these equations, substitute here, and then using a calculator or something do the calculations. Okay. whereas Excel or even GraphPad can do if you are given raw data. What does that raw data means? For example, if you are talking about 10 rats, I will have all the 10 var value, no, 0.0045, 0.0048 like that, and if I have 8 mouse, I will have all the 8 var values, whereas here the average and standard deviation of this 10 data set is given. That means somebody has already done that calculation and given you. So the Excels or GraphPad will not be able to handle this type of data, so you need to use these equations. Okay. So we talked about 2 sample t-test where you can compare 2 different sets of samples, and I told you how to calculate the t using this equation, and you say whether the equation t is greater than the t in the table for a one tail or a two tail test. If it is greater than the table, we reject the null hypothesis. If it is less than the t table, we accept the null hypothesis. Okay. So and also we looked at one tail test where we are saying that the drug induces sleep much faster than placebo. They were in the valve when they are implanted in rats is much more, and so on actually. Okay. So in that sort of thing we are talking about one tail test. Okay. So I also showed you the table, how to use the table, and that is very important. In that table it tells you the p values for one tail on the top and the p values for a two tail here, and this one gives you the degrees of freedom. In a 2 sample t-test, please remember the degrees of freedom will be number of samples for sample set 1 and number of samples for sample set 2 minus 2. Okay, remember that. Whereas when you are doing one sample t-test, it will be total number of samples minus 1, that will be the number of degrees of freedom. Okay, so we will continue and we will talk about pair t-test in the next class. Okay, thank you very much for your time.